All right, hi you guys. Here is a quick review of some of the topics that you guys did in Math 2 last year, but it's been a long time and we just tend to forget those things that we haven't practiced lately or that maybe we've only seen once and still haven't practiced. So I took note of some of those things that are showing up in your homework that I'm getting a lot of questions about, which is normal since you guys haven't seen this stuff in a while. So it's pretty important that we get this stuff figured out because we will see this continue in our homework and possibly on some tests as well. So I have 4 main review topics, the first being right triangle trigonometry. And I'm using this live document camera because I want to show you my calculator for a couple of these problems as well. So let's start with reviewing trig ratios. So in Math 2, 3 trig ratios were introduced that relate a right triangle's acute angles, so these smaller angles and side lengths together. So this angle is related to ratios of these 3 sides as well as this angle. And those are the 3 trig functions that you guys were introduced to last year: sine, cosine, and tangent. So let's review what those 3 ratios are. So this sine of an angle, so in this case, it's this angle. Let's clarify the 3 sides. So we have hypotenuse, which is the opposite of the right angle. The side opposite is wherever my theta, whatever angle I'm interested in, the opposite side is across from it, and the adjacent side is next to it. So if this is theta, this side length is adjacent, this side length is opposite, and this is always the hypotenuse. So the sine of a function is, or the sine of an angle is the ratio of the length of the sides opposite divided by hypotenuse. So opposite divided by the hypotenuse. And tangent, we'll jump to cosine. Cosine is the adjacent side divided by the hypotenuse. And the tangent is the side opposite divided by adjacent. And these are the side lengths. So opposite divided by adjacent. So that's a lot to remember, these 3 ratios. So that's why you guys hopefully are familiar with the phrase SOHCAHTOA, which is a made-up phrase that uses the letters of sine, cosine, and tangent. So SOHCAHTOA is the helpful way, SOHCAHTOA. So sine, this is sine, is the opposite over hypotenuse. Cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So this is the helpful way that to this day I still remember those ratios. So let's look at a couple of examples. So I'm going to show you a couple of examples and then skip to the next topic, and your homework will be completing those examples where it says your turn. So let's look at example 1. Use the sine inverse. So that little -1 means inverse sine. Use inverse sine, inverse cosine, and inverse tangent buttons on your calculator to calculate the value of theta, rounding to the nearest hundredth. So when I look at this right triangle, and this is the angle that I'm interested in, I want to find the value of that angle measure. Well, I'm given two side lengths of this triangle. I'm given the side opposite of 13 and the hypotenuse of 19. So then I would go back to SOHCAHTOA and figure out which one of those 3 trig ratios relates to the sides opposite and hypotenuse. And where I see this O and H for opposite and hypotenuse indicates I'm going to use the sine function. So the sine of my angle, theta, equals the side opposite, 13, divided by the hypotenuse, 19. So now I want to figure out what theta is. And to undo this sine function, sine is not a value. It's not a number I can divide by. I can't divide by just sine. Sine is a function of a variable, theta. So I want to get that variable solved for by itself. So I need to undo the sine function, and that's where the inverse sine comes in. So the function that undoes sine is sine inverse. And when I apply that to both sides, I'll get theta on the left, but now I need to find the inverse sine of 13/19, and that's where our calculator comes in. On a graphing calculator or scientific calculator, the first thing is you need to make sure you're in degree mode. So on a graphing calculator, when I hit this mode button right here in the top row, if you look right here, if I arrow down, it's currently highlighting radian. That means I'm in radian mode, but I want to be in degree mode, meaning I want my answers to be in terms of degrees. So I'm going to select degrees. Now I can find the inverse sine of 13/19. So the inverse sine button, here I have the sine, cosine, and tangent buttons right here. And the inverse sine is the function that I would get when I hit second sine. So when I hit second sine, you see the inverse sine pop up, 13 divided by 19, and I get 43.17 degrees. Let's look at another one similar to this. So here's my angle theta that I want to figure out the value of. I know the side length opposite, that's opposite, and I have the side length right next to it, which is adjacent. So then I would look up to my SOHCAHTOA and think which trig function, sine, cosine, or tangent, relates the opposite and adjacent sides of an acute angle in a right triangle, and that would be the tangent. So I would set up my equation. The tangent of theta, equals opposite 24/8. And I want to get theta by itself, but right now it's stuck inside the tangent function. So to undo that, I need inverse tangent. When I take the inverse tangent of this side, I get theta by itself. And when I take the inverse tangent of the other side, I'll use my calculator. So again, inverse tangent is right here. Right here. So I hit second tangent to get the inverse tangent, and then type in 24 divided by 8. And I get 71.57 if I round. So 71.57 degrees. Okay, let's look at another type of problem, and that's where I'm actually given the value of theta, 15 degrees, but I don't know the side length. So it's kind of opposite. Here I knew two sides, but I didn't know the angle. Here I know the angle in one side, and I want to know this other side. So it's going to be the same strategy. The angle that I do know is opposite of the side I don't know and adjacent to the side I do know. So that's going to be the tangent function again, OA, when I go back up here to my SOHCAHTOA. So the tangent of 15, I know the degree measure now is 15 degrees. The tangent of 15 degrees equals opposite y over 38. So now I just need to solve for y. Right now y is being divided by 38. So to undo that, I would multiply both sides by 38, so it cancels here. And I multiply by 38 here. So all I have to do is use my calculator. Again, make sure you're in degree mode so that it actually computes tangent of 15 degrees as opposed to 15 radians. And we type in 38 times the tangent of 15. So this time, instead of using inverse tangent, I'm just using the tangent function right here. And I get that value of 10.18 units. 10.2 units. Let's look at one more. So jumping over here to this one, I've got a 49-degree angle. I know the hypotenuse is 23, the side opposite of my right angle, and I don't know the side adjacent to it. So A and H, looking back at SOHCAHTOA, that's going to be the cosine, CAH. So the cosine of 49 degrees is opposite, nope, it's not. So adjacent x over hypotenuse 23. So to solve for x, which is currently being divided by 23. I would undo that by multiplying both sides by 23. So now I have x equals 23 times the cosine at 49 degrees. So I would just type in 23 times 49. And I get 15.1. So that's the side length of x. Okay, so that's a quick, brief review. I know you guys were introduced to this stuff last year. It's been a while. This SOHCAHTOA is the most helpful thing that you guys will have when it comes to using trig ratios to solve unknown lengths and angles. So your turn, show your work, show me the steps in solving for the variables in these problems, as well as on this next page, we are gonna move on to simplifying radical expressions. So I know you guys just love radical expressions and square roots when you don't have a perfect square on the inside. So we're gonna address that and get some practice in. So typically you guys like saying something like this, the square root of 25, because 25 is a perfect square, so it's a simple answer of 5 when I simplify that. But it's not always going to be that easy. So let's start with an example, the square root of 40. So 40 is not a perfect square, but I do know that I could rewrite 40 as a perfect square times another number, since 40 is divisible by 4. And I know 4 is a perfect square. So I can, and I do know this square root of 4 is broken up by multiplication, one individually. So the square root of 4 is 2. So that 2 is going to come out of the square root and be out front. So this would be 2 times the square root of 10, which is still not a perfect square, nor is it divisible by any perfect squares. So we're going to leave it like that. I can't break down the square root of 10 anymore because it's only divisible by 2 and 5, neither of which are perfect squares. So let's look at another example, the square root of 72. I don't think 72 is a perfect square, and if I wasn't later and don't get this decimal, which tells me it's not a perfect square, but it might be divisible by a perfect square. So I'm going to rewrite it as the product. Let's see, I know 4 is a perfect square, so first I would check to see is 72 divisible by 4, and I can see that it is. So I can rewrite 72 as 4 times 18. I know the square root of 4 is 2, so that 2 is going to come out. So I have 2 times the square root of 18. But this isn't totally simplified. 18 is not a perfect square. However, it is also divisible by a perfect square. I could divide 18 by 9, which is a perfect square. So again, I'm going to rewrite the 18, the square root of 9 times 2. The square root of 9 is 3. So the 3 is going to come out front, and I'm going to multiply it by whatever else is already out there. So I have 3 times 2 on the outside, which is 6, and 2 left on the inside, which I cannot simplify anymore. So hopefully this is a good refresher on how to do that. Now let's look at the square root of -1. So you guys are used to me saying, oh, we can't take the square root of real negative numbers because then our result would be a non-real result. But I think you guys were introduced to square root of -1 last year. And the square root of -1, while it's not defined within the set of real numbers, it is still a value that's useful in computing different things, specifically in different fields of engineering. So while we typically avoid taking the square root of negative, it is a value that's used in real life. So imaginary is kind of misleading. It's what technically is called a complex number. And the square root of -1 we write as I. So when looking at an example like number 4, the square root of -36. 36 is a perfect square. its square root is 6. And the square root of -1 is I. So since negative 36, you could think of it as -1 times 36. I'm going to take the square root of both of those. The square root of -1 is I, and the square root of 36 is 6. So this simplifies to just 6I. So let's look at one that's not a perfect square, the square root of -75. 75 is not a perfect square, but I can break it down to 25 times 5. And I've just left the negative out front. The square root of 25 is 5, so the 5 can come out. And the square root of -1 is I, so the I can come out, and those are multiplied together. So then I just have this 5 left on the inside. So the square root of -75 equals 5 times I times the square root of 5. All right, so what if we want to add or subtract? You can add or subtract, in this case, root 3, kind of like you would if if it was replaced by an x. Like if I had 2x minus 5x, you would combine those to say, okay, 2x minus 5x, that's -3x. So that's how you can think of these root 3s. If they're exactly the same, you're just going to combine them together. They're considered like terms. So 2 root 3s minus 5 root 3s is -3 root 3s. So if I'm looking at an example like number 7, I've got -3 root 20 plus 7 root 5. Those are not the same roots. So I can't just combine these together by adding the -3 and the 7. But I could simplify the square root of 20 first, and then I'll be able to combine these. So let me start by just rewriting this as -3 times the square root of 20 can be broken down into 4 times 5. And then I have plus 7 root 5. So the square root of 4 is 2, which is going to be multiplied by our -3. And then I have the square root of 5 left. So 2 times -3 is -6 root 5 plus 7 root 5. Now I have this same like term of the square root of 5. So I'm just going to take the -6 root 5s that I have here, add 7 to that, 7 root 5s to that, and then I end up with +1 times the square root of 5, which is just the square root of 5. Hopefully this was a good refresher on dealing with these square roots of non-perfect square roots of non-perfect and decent. This was a good refresher on dealing with these square roots of non-perfect by the equation y equals a times b. Hopefully this looks somewhat familiar. A is always what we call the initial value of some at the beginning of a time period. And b, the x, so what x is, that's however many times multiplied by b, so that's called the multiplier. So let's look at some examples. Jimmy's baseball card collection is currently worth $1,400 and is expected to increase by 4% starting value. That's what something is worth now. So that's my value of A. It's increasing by a value of 4%. So we need to take this percentage and convert it to a decimal. 4% to convert to a decimal, we take what we would imagine putting a decimal after it and move it over 2 times. essentially dividing it by 100. So 4% is the same as 0.4. But that can, because if something is increasing, that doesn't make sense if I'm multiplying by a number less than 1. So a multiplier is always this much larger than 1. Think about 104% of something. So the multiplier is always you add or subtract that percentage from 1, depending if it's increasing or decreasing. Since it's increasing, we would add it. So the multiplier is 1.04. So I know A, I know B, and I want to know how much this is worth in 10 years. That's in y equals ax. We can now fill in these values. $1,400 times the multiplier of 1.04 for 10 years in a row. So I would crunch those numbers on my calculator. $1,400 times 1.04 raised to the 10th. So those would be worth $2,072.34, 10 years later. $2,000. All right, let's take a look at one more before you try a few on your own. So Liv bought a car for $5,000. That would be my initial value. The car's value is expected to depreciate. Depreciate means it's going down. Depreciate is the opposite of appreciate, which is increase in value. So it's going down in value by 12% every year. How much will her car be worth in 7 years? So my multiplier is not 12. Hi. Oh, hi. That was Roseanne. She didn't know I was recording. So my multiplier is not 12. Remember, this is the percentage. I need the decimal for 12%, which is 0.12. But my multiplier isn't 0.12 either. I need to take 0.12 and subtract it from 1. So my multiplier would be 1 minus 0.12. So imagine taking 12 away from 100. That would be 88. So 0.12 1 minus 0.12 equals 0.88. So my multiplier is 0.88. So my equation, y equals a, my initial value of 5,000, times my multiplier, 0.88. Think about multiplying by that. It's definitely going to decrease since it's less than 1. And how much will it be worth in 7 years? So I would type that in, 5,000, 0.88 raised to the 7th power, $2,000, $2,043.38. 2,043.38. Okay, hopefully this is ringing a bell also from what you guys have learned about this type of problem. And we are going to move on to our final review topic that I see lots of mistakes on and want to address, properties of exponents. Properties of exponents is something you guys have probably been learned or working on since Math 1. But again, it's that type of thing that just takes repetition and practice. So let's review very quickly the main properties here. If I have the same base x and I've got those different x's or those x's raised to different powers, but they're being multiplied. X to the a times x to the b is x to the a plus b. So that is the same as a raised to the power of the sum of whatever those are. Conversely, if I have x to the a divided by x to the b, the result would be the same as x to the a minus b. And this should make sense. For example, if I had x squared times x cubed, think about what that would be. That would be x times x times x times x times x. So basically, I'm multiplying x by itself a total of 5 times, x times x times x times x times x. That's why I take my exponents and add them. So it has to be the same base in order to do that. Same with subtraction. If I have x cubed divided by x squared, think about what that means. It's x times x times x divided by x times x. And x divided by itself is 1, so that's 1. X divided by this x is also 1. And I'm left with x to the first, which is the same as x to the 3 minus 2. So if you forget these properties, you could just expand them and do this the long way, but the properties help us with these shortcuts. A number raised to a negative exponent, that does not mean the result is negative. In fact, it's not going to be negative. What this is the same as 1 divided by x to the positive a. So for example, if I have x to the negative 6th, that's the same as 1 over x to the 6th. A power raised to a power, that would be the same as x to the a times b. And then lastly, if I've got a negative exponent on the something being raised to a negative exponent, so we addressed that here, it'd be the same as a fraction. But if I have a fraction already on the inside of those parentheses, this is the same. I could make that a positive exponent if I just swap a and b. In other words, take the reciprocal. So a over b raised to the negative c should be rewritten as b over a to the positive c. Okay, 3 examples. So right here I've got a whole bunch of stuff. Obviously these are way more complicated looking than our properties, but we're going to apply multiple properties in every single problem. So the first thing I have here is a bunch of stuff being raised to the negative 1. So I'm going to apply this property, something being raised to a power, I multiply the powers. But I have multiple things being raised to this power. So I'm going to raise every single thing to the negative 1. 2 to the negative 1 times x to the 4th to the negative 1. So I'm going to multiply 4 and negative 1. So 4 to the negative 1 times 3, or y to the negative 3 to the negative 1. Negative 3 times negative 1 is positive 3. So I'm not done yet because I have negative exponents, and when you simplify exponents, you don't want any negatives left. So again, we're going to apply this property now. Something raised to a negative power, I'm going to rewrite it as a fraction. So 2 raised to the negative 1 is the same as 1 over 2 to the positive 1. Whoops, I don't know why this magically turned into a 4. It's x to the 4th to the negative 1 is x to the negative 4. So I'm going to rewrite x to the negative 4 as 1 over x to the positive 4. And then I have y cubed, which since 3 is positive is actually going to be not in a fraction, or you could think of it as y cubed over 1. Now I can just multiply my numerators, 1 times 1 times 1, which is y cubed, divided by my denominators, 2 times x to the 4th times 1, which is 2x to the 4th. All right, so the next one, I have a whole bunch of stuff going on here. First, I have this set of parentheses squared, and then this set of parentheses raised to the 1/2. That's one I actually forgot to show you, so I'm going to include one extra property here. Something raised to a fractional exponent, like x to the 1 over anything, to the 1 over a. That's the same as the a-th root of x. Let me give you an example. X to the 1/3 is the same as the cube root of x. So this being raised to the 1/2 is actually just the square root of that. So first I'm going to take my first set of numbers and square everything in there. I'm squaring 3 and I'm squaring a. 3 squared is 9, a squared is a squared. Now I'm going to take everything in this set, I've got 3 terms in there, and raise everything to the 1/2 power. 25 to the 1/2, which we know is, again, the 1/2 power is the same as the square root. So I'll write it like that. Times a squared to the 1/2, or the square root of a squared, times b to the 1/2, which is the square root of b. So 9a squared times Square root of 25 is 5. The square root of a squared is a, times the square root of b. Now I've got 9 times a squared times 5 times a. Because this is multiplication, we can switch the order. So I can actually go ahead and do the 9 times 5, which is 45, and a squared times a, which is a cubed. And then I've got the square root of b next to it. All right, one last example here. I've got 4 x to the 0, y to the negative 2, z cubed, all over 4x. There's lots of simplifying we can do here. The first thing is that I notice I have 4 in the numerator, 4 in the denominator. 4 divided by 4 is 1. So I can actually pretend that's not even there, since 4 divided by 4 is 1. Also, x to the 0 is also 1, which is nice. I can cancel that out. Anything raised to the 0. So I forgot to show you that property, and here's another property. Anything raised to the 0 power equals 1, always. So now I have y to the negative 2 z cubed divided by x. So let me start by rewriting that. I'm almost done here, except I have a negative exponent. That's not, we can't leave negative exponents. Y to the negative 2 is the same as writing 1 over y squared. So that's this basically means this whole thing goes down here in the denominator, but with a positive exponent. So my numerator just has z cubed left in it. And then y squared got moved to the bottom, but it can be a positive 2 now, times x. And that is how that simplifies. So there's a very quick, brief review on lots of topics that have been showing up in your homework that I've been getting questions on. I wanted to address this because you will see some of these concepts continue to show up both on homework and potentially on tests as well. So hopefully that clears up any confusion and gives you a good refresher. So your homework is to finish all of the problems under the Your Turn section. So these three, these 4, these 2, and then on the very back, I have 5 properties of exponents. So once you're done, I would like you to submit these to Schoology, and then you're done. All right, have a great rest of your day. Adios.